Good morning, good afternoon, and good evening to all those attending. Welcome in this Rilem Rock and Talk webinar, where we're going to be talking about concrete cracking and more specifically, why crack control in reinforced concrete can be considered an intricate art. As a matter of very quickly introducing ourselves, this talk will be delivered by Miguel Azenha and myself, Fragkoulis Kanavaris. Miguel is an associate professor in the University of Minho in Portugal and has dedicated much of his research career in understanding concrete cracking from a design experimentation perspective. And I'm ARUP's leading concrete expert based in London, in the UK, and have also worked for several years in crack control of concrete, both on research and design level. Between us, we lead Rilem TC287 CCS, the Rilem Technical Committee dedicated to pretty much anything related with crack width control in concrete. When we're talking about cracking, there are several matters regarding the nature of cracks that should be considered. That commonly shown figure from the UK Concrete Society denotes qualitatively the most common types of cracking. For example, there are cracks which develop during concrete's plastic state, plastic shrinkage, plastic settlement, or crazing cracks, and those from other effects, such as alkali-silica reaction, reinforcement, corrosion. However, the quite critical ones that we are going to be looking as part of this webinar and shown with blue arrows are those related to restrained thermal and shrinkage deformations as well as applied loads. The reason is that restrained cracks often require contribution of reinforcement to control them, while cracks of other nature are normally managed and mitigated through good concrete quality, concrete technology, and good workmanship. And this is a quite particular aspect in reinforced concrete engineering, where interconnection between material science and structural engineering is of paramount importance. So we need those superpowers in terms of knowledge from both disciplines to be interconnected, which is something that does not take place as frequently as we want it to take place, and we'll be touching on that during this webinar. So what are the intricacies of the art of crack width control in concrete? They mainly originate from how the cracks would be formed, and that also dictates the mitigation approach for these cracks. Firstly, we can have massive concrete fractures where residual stresses are developed due to early age hydration temperatures, such as what we get in massive concrete foundations and other massive types of structures such as dams. And then we get stresses that develop in most, if not all, concrete structures due to the combination of applied loads and restrained deformations. And in this scenario, shrinkage and creep are very hard to predict, and many are also the variables and complexities to consider. For the rest of the presentation, we will assume that we're not dealing with massive concrete structures, but if we did, we have developed several good resources that would assist one to understand when a structure is a massive structure and how crack control should be approached, as massive structures do have their own peculiarities when it's going down to controlling cracks and controlling temperatures.
So now, why would this be an art? And that's a very relevant question. And I must remind you what Fragkoulis just mentioned is that we are not looking into massive structures aspects such as early age stresses. This is what I noticed in the top-hand side of the presentation. However, even thinking only about combined load and restrained deformations, we still consider this to be an intricate art. So I will go through these bullets that we have in the slides. So the first of all is that this is not really something that we teach in general reinforced concrete structures courses. I do not do it myself. There's normally no time in the programs to go to this level of depth. So for that reason, and to my best knowledge in most universities in the world, this topic ends up being sort of too complicated, and it's on a postgraduate situation rather than in the general courses. So the society in general in engineering doesn't know pretty much how to handle this. So the second aspect, also already mentioned, is that we need an intricate knowledge of material science and structural design. So it's not only about prescribing the concrete class, because there's so much more to it, to understanding what's the origin of the behavior of the material in terms of shrinkage, in terms of creep, for example, and also how it will interplay with the surrounding environmental conditions. And all of this stems from knowledge in material science that will need to be an ally in structural design so that we can do competent assessments And there's another further complication that makes this even a more of an intricate art, is the challenges of new mixtures. And by new mixtures, I'm not speaking about recycled aggregates or such like. I'm speaking about the fact that many of our traditions that were very good in mitigating the proneness of cracking, such as the use of fly ash in our mixes, is disappearing for good reasons. It's that we are no longer using, or at least we are trying to no longer use coal to produce energy. And because of that fact, we will not have as much fly ash that as we had before. So for that reason, and even speaking about my personal experience, I've been witnessing significant numbers of situations where cracking starts to happen when experienced engineers on site and designers as well were witnessing normal situations in the past, but with these new mixes, they are witnessing cracking. And then the sentence I mentioned several times when I was a designer in the beginning of my career, I followed everything that was in the regulation, Eurocode or not, and this still is cracking to an admissible level. Why? And the reason is simple. The regulations are oversimplified for the complexity of the situation. And even if we look at specialized literature like Syria C766, which is an amazing report, it might still lack the necessary generality to be applied to all situations, because good judgment is fundamental to every single situation of this kind. So for that matter, also a last aspect that even brings this further to an art. What is really a crack? And most importantly, what would be the acceptable width that the crack could have for a certain performance requirement? And regulations are not there yet. Regulations are transmitting some kind of consensus that a group of people have arrived to. However, this consensus many of the times is rather conservative. And to go deeper in this matter, there's a very interesting review we did recently on the effects of cracking and crack width on corrosion of reinforcement in concrete, where we realized that even as of today, we don't have a unified judgment about this. So this is really complicated on several levels. But going on, I will just do a little bit of an insight into what I normally teach to my normal reinforced concrete students. And sorry for the language here, we have a couple of Portuguese things, but you understand it's stage 1 and stage 2. But the biggest thing I want to point with a mouse, I will go through several aspects of this graphic, but I will be relatively quick. We have a tie. This tie is under controlled force testing. So we will increase the force monotonically along an experiment. And during this experiment, we are recording the force and we are recording the average strain on the system. And this will be recorded also in terms of the steel stress and the concrete stress, as well as the strain in both materials. And of course, before cracking, this is very simple. The concrete has a certain tensile stress, and the steel has another, which is a number of times bigger according to the homogenization between the two materials. And eventually we reach in the concrete the tensile strength. A crack will happen somewhere where there's a fragility. And here's an example of where it could happen. Here it is. So the crack happens and you have an increase of stress in steel, a decrease in stress in concrete, and naturally a disturbance in the field of strains. And of course, a loss of stiffness in the system because suddenly it almost goes flat. And then what is interesting here is this distance between the crack and the point where the system doesn't even know that there was a crack. So to the left of this distance S, we have an homogeneous stress state in steel and concrete, meaning that the bond was enough to bring the stresses in steel from a maximum to the average, I would say, and in the concrete from 0 to the average, I would say. So now the places in the concrete where we are in position to get a new crack are this left-hand side and this right-hand side. The next crack, of course, in this example that I created, is happening there. It's not by chance, actually. I did it on purpose to be twice as much that previous distance. I go to the previous slide. There was a distance S, and the next crack will happen at 1.99, because S is the minimum spacing between cracking, and 1.99 of that would be, which was twice, almost twice, would be the maximum. This means that the stress in concrete cannot reach enough state to generate another crack. So this is the maximum crack spacing. And then to the left, there's no way we can get a new crack because the stress will not be able to increase. And only we can get a new crack on this right-hand side. And this is exactly what happens. A new crack will happen in somewhere there. It did happen. Now, this flat line would be actually a little bit sloped up. This is a symbolic representation. But now we see that there's nowhere in the specimen where we have a stress that is high enough to reach the tensile strength of concrete, even if we increase force in steel. And that's actually what's happening. As the axial force increases, now we perceive a behavior that we all, or at least most of us know, which is the tension stiffening effect. So we have a stiffness that is now not affected by the development of new cracks, but we call this the stabilized cracking stage. And we have a behavior very similar to the bare steel covered by a little bit of reinforcement here and, a little bit of concrete here and there. And nowadays, the calculation of strains and crack widths in all regulations worldwide are generally devoted to this stage, which is called stabilized cracking stage. And this is one of the challenges that we suffer in the art of cracking of concrete in service. Because when we are having cracking because of imposed deformations such as shrinkage, we will not normally reach the stabilized cracking stage, which means that our equations, our approaches that we have in regulations are not actually proper for that situation. Then, furthermore from that, we know that imposed deformations such as shrinkage are not really uniform throughout the thickness of specimens or thickness of members, because we drive from the outside towards the inside. So we have a different stress state because the concrete on the surface wants to contract, but in the inside, it doesn't want to contract yet. And we'll get uneven tendencies of strain. And of course, we will get the consequent situation where we have the stresses happening. So this is taken care in regulations normally by a coefficient, which is actually not really how we should do it because it's more complex than that. Then we have primary and secondary cracks when we have imposed deformations. I'll not go deeper into that, but that's also an issue where the patterns have an interplay there. And finally, the last interplay, which is creep and shrinkage, which has been spoken about, so I will not go deeper into that. Okay, and also, this is just to provide you with an insight that this is, we are not just showing our opinions, we are showing actual experience from things that happened in the past. And one of the things that happened in the past is that we launched a benchmark between several design offices, so structural design offices, experienced engineers, and they were actually challenged to size the reinforcement needed for a very long slab of 50 meters length and with spans of 5 meters. And the slab would be not very thick, so a 15 centimeter slab supported on 50 centimeter beams. And we came to the conclusion that when we asked them, please detail the reinforcement to do this and give us the quantity and the layout, there were differences in the layout, but fundamentally there were differences in the quantity. So someone here was over designing, someone here might have been under designing, we don't know, or everyone is totally wrong. So and they were all following their ensemble or their mix of regulations that they thought were the best to follow or their own experience. So this is definitely something, this was maybe 5, 6, 7 years ago. It's not that long ago. So this is something we need to attend to.
So we did find the results, pardon me, from the study that Miguel shared quite interesting. And we decided to take a step back to understand what the regulations are telling us. And from investigating different key regulations across the world in all continents, it appeared that there are significant differences with the crack width predictability of each different code and guidance document and the reinforcement requirement to control cracks at a certain width. This can have a direct effect on the serviceability and durability of the structure, but also on the sustainability of the structure or of the element that we're designing, as the amount of material, in this case, steel, reinforcing steel that is used to control crack width, can vary significantly. And if we're not capable of coming to a consensus as to which one is the particular method that we should be adopting, we end up with designs across the world with varying embodied carbon and varying materials usage, while the durability and their serviceability is not guaranteed. It should be acknowledged that analytical approaches such as those in standards are must-haves, they're mandatory to exist to facilitate design, but information for fundamental behavior can be obtained mainly from numerical simulation. As part of the cost action to U1404, several numerical benchmarks were conducted, showing the importance of numerical simulation in controlling cracks, but also the variability of different modeling approaches when it comes to modeling hydration and shrinkage, and things can become quite complicated in that regard. The optimum numerical analysis should actually include thermal, shrinkage, and creep effects as restrained by boundary conditions. As part of a couple of studies modeling the relatively well-known restraint and shrinkage ring tests, it was found that appropriate selection and calibration of creep and shrinkage models is critical towards predicting cracking representatively and accounting for the special effects of differential shrinkage that were previously mentioned with Miguel, and they are known to contribute to superficial or not superficial cracking in reinforced concrete structures. And speaking of tests, apart from analytical and numerical approaches for understanding and predicting cracking, special restraining devices have been developed over the years to actually simulate restraint cracking effects in the laboratory. These vary in terms of complexity and mechanisms. For example, there are passive systems where a concrete specimen is cast in a restraining device and left to crack for a period of time, such as the ring test or some other longitudinal devices and the cracking frames. And then there are other types of specimens where the restraint is actually actively controlled throughout the testing duration in order to get more information of how a crack would develop with the variable restraint scenarios. If we want to find out more, we did carry out a review study on that topic a few years ago, which is quite all-encompassing in this kind of restraining devices framework. But what we were really missing was how to account for combinations of restraint deformations and loading in terms of testing in a laboratory environment.
Yes, and that was precisely the purpose of a set of research that was carried out a few years ago in the University of Minho, which to our best knowledge so far has been the single experiment to combine at the same time the effect of restraint deformation together with perpendicularly applied loads that create bending in the specimen. So this is what we did. So a specimen, a slab-like specimen that is actually 50 centimeters wide, 10 centimeters thick, and 2.4 meters span between the two supports that you see on the picture. So there are two transversal rods that you see here. They go throughout the slab, and this slab is simply supported with 2.4 meters span, and it will be loaded transversely. But at the same time, interestingly, we created a device that will make that the rod on the left-hand side, so here on the picture, this rod will be pushed or pulled, whatever we want. We can do it both directions, but when you are restraining what you want to actually restrain it from shrinking, and so you have to push in that case, and this will create a state of controlled restraint that we can do it in the experimental facility. At the same time, it will allow to put applied loads. What we were simulating here was a 2.4 meter span in the simply supported region of an hypothetically existing 4 meter long beam, continuous beam, meaning, or continuous slab, I apologize. And this continuous slab is not that different from reality in the sense that we managed to do it with a 10 centimeter thick. We wanted to do 15, but yeah, that was a different scale in the lab. But we did a 10 centimeter thickness and with rebars of 8 spaced by 100 millimeters. So we sized it according to the Eurocode by overlooking the effect of shrinkage and I mean the restraint shrinkage. As a designer, we would not be worried about the process. And then we carried out the experiment. The experiment included 4 slabs, actually. One slab where we had, at the same time, the restraint deformation and the applied load with these prisms that we put on top, serviceability load, clearly. Of course, this was inside the climatic chamber. A second slab where we only restrained longitudinally, but transversally, we had the effect of self-weight, of course, but much less than slab number 1. On the third slab, we had no restraint to the deformation, yet we had the bending happening, so the load was applied. And the fourth slab, which we call the dummy, where there was no restraint to deformation, at least not external, and there was no applied load. So we measured the behavior of all this with several devices, and I will not go into details. These are just illustrating pictures. Also, it created the need for a very intricate set of casting and care for curing and for the early ages, because all of this was really important to make sure that the experiment was traceable. And ultimately, at the age of 50 days, we applied a quasi-permanent load combination with the load that you see on screen, and we made sure that the load was applied uniformly and progressively, and we monitored all the process. This was really interesting to get the behavior, which is, of course, published for those that want to go more into detail. What I would like now to state is that the experiment ended up being successful. This is the last slide I'm presenting about this experiment. Of course, there were cracks on the support area, but regarding the three slabs where we had slab number one, which had axial restraint and bending, slab number two, which only had axial restraint and very small bending, and slab number three, which had only bending, they got the behavior that we were expecting. So slab number one clearly cracked more, of course, and which was more restrained and with more load, and yet the cracking was actually bigger than the crack that we anticipated when we overlooked the shrinkage. Yet it was not that much bigger. And then this was the ground for next research that happened. But still, for those wanting to go deeper, this is published material where we even have simulations where we learn more about it. But speaking about simulations, I would like to draw your attention to something that was already presented in this presentation, sorry for the repetition, which is this system that we had a benchmark a few years ago for designers to compare the behavior of their models. And what we did was a full 3D thermohygromechanical analysis, which is, in my view, the most complicated thing that you can do at macroscopic scale with the people that are actually getting results for the structural level. So we modeled this slab with symmetry, of course, supported on beams and in a very continuous system and highly restrained. We made the thermal and hydro simulation with 1D models because this would be simpler and quicker to calculate, and it's a published work. Of course, with that, we could have the driving forces from the humidity not being uniform in the system, and computing from the humidity, the tendency to shrink, which is bigger in the surface than in the inside in a normal strength concrete. I mean, there was not big autogenous deformation. Also, we took into account the temperature field in this case, even though there was not a big change in temperatures during the early ages. There were 7 to 10 degrees change. So this was causing some stress in the beginning. And ultimately, the most important thing that we concluded, and I think this is really important that we managed to report it in a scientific and coherent manner, was the comparison of the force that will cause the cracks in a theoretical model. So if you think of a theoretical model and you have this axial restraint, you will compute the cracking force just by saying it's the area of concrete multiplied by the tensile strength of concrete. And then you have the cracking force. And this would be, in theory, if you even following the regulations, you will compute the cracking force by doing this. There will be a coefficient there, but they don't change it much. And what we realized, and this is something that many engineers also do it by heart, is that the real force that happens is almost half of that in most conditions. We see here several simulations, but I will not go into that detail. But what happened is, upon cracking, the maximum force that happened in a restrained system with many complexities such as loading, non-uniform shrinkage, and etc. So the shrinkage was coming from the surface to the inside. And it was concluded that it was roughly 50% of the theoretically expected with a very simple model. And this was because of a combination of effects. We have this all in the publication, well discussed, in my opinion. But the main thing is the fact that the shrinkage, in this case, was drying shrinkage was non-uniform. So we had more shrinkage on the surface than on the inside. So it created an initial stage of cracking only on the surface. And this bigger crack that happened when the restraint was big enough to cause the cracking of the entire specimen or the entire slab, a part of the slab was already cracked. And the bending altogether with this even have some beneficial factors together with the creep. And all of this together reach to something that allows us to save reinforcement. And this is a very important conclusion that we are following up with further research, but this combines with many designers that do this by intuition.
Quickly going back to analytical approaches before actually closing, there are some alternative methods for prac control already applied in certain parts of Europe, specifically Germany and Austria. These are based more on mechanically consistent models compared to the calibrated models, which are inherent in all major codes, including Eurocode. But I would say that they're not yet as straightforward for using as the other models, which are more widely adopted. And that actually brings us to the conclusions and final considerations for this webinar. I believe we've demonstrated that the reinforced concrete serviceability cracking is not a solved problem, but it is a quite relevant one for durability, lifespan, and the sustainability of concrete structures. We do encompass the knowledge and pathways to deliver optimized solutions, but these are not generally mastered by many across the world. We desperately need the combination of structural and materials engineering to reach to optimum solutions. And when we're looking for future developments, the requirement for widespread training and knowledge is quite critical, and also is the requirement for more regulations, either updated ones or even new ones, having more refreshed look at the matter. As we've shown previously, there is great variability between different models and different codes across the world. So we do need to obtain convergence, let's say, for consensus on those approaches. And ultimately, we will have to consider the implications with alternative binders and reinforcing materials, because with the current urgency to use environmentally friendly alternatives, both for binders and reinforcing materials, we're delving into territories of uncharted waters, and we don't know whether the existing models will be actually reliable enough for use with novel binders and reinforcing materials. That being said, as part of the Rilem Technical Committee 287 CCS, a quite comprehensive guidance book will be coming out soon, looking at exactly the topic of early age and long-term crack width analysis of reinforced concrete structures. And I would say that it's probably one of the most comprehensive books and guidance on the subject over the past few years. So do watch this space if you're interested. And I think I would speak for both of us. Miguel, we wouldn't be here if it weren't for the dedicated contribution and involuntary contribution from many Rilem members, from at least 2 Rilem committees, and from other collaborators and co-authors who couldn't be included in the list because of space limitations, but are gratefully acknowledged for their contribution. And on that note, we would like to thank you for your attention and take any questions you might have.